I hope everybody can see. Okay, cool. So what I will be talking about is single top production, but associated with a Higgs boson. And most of the work is an effective field theory approach. So this is a work which is in preparation and with my advisor, Dr. Woodcup, and two other collaborators back from my home country in India. Okay, so the first question that we might ask is why are we studying effective field theories? And we know that the standard model has been tested to a great precision. It's quite a success story, but the general consensus is that it is more of an effective theory, which holds up to a certain energy scale, beyond which we might encounter some kind of new physics. Um, so, from the current experimental limits that we have, in most cases, we are allowed to probe for new physics using particles that we already know. And in that case, and also for some of the theories which we already know, for example, supersymmetry or any other higher dimensional theories, sometimes it is easier to kind of ignore certain kinds of certain degrees of freedom and get to a more simplified theory, and we integrate out those degrees of freedom and end up with an effective theory at a lower energy. So effective theories are kind of a way of parametrizing what we don't know yet about physics that might lie at certain energy scales much higher than the experimental probe of today's experiments. Okay, so next let's talk about the building blocks for any effective field theory. So what we assume is that there exists some kind of new physics beyond some energy scale that we denote by lambda. And that new physics, whatever that is, respects the standard model local symmetry. So the SU3 cross SU2 cross U1, that local symmetry is present even for the new physics. Next, we assume that the new physics is weakly coupled. So, and at low energies, it reduces to our known standard model. So any heavy particle that might be present at order lambda or higher kind of decouples from the theory. And what we are left with is just the standard model Lagrangian in 4 dimensions and a bunch of higher dimensional operators that are all suppressed by powers of lambda. So each term will have two different parameters that we can say. One is the scale of the new physics, lambda, as I mentioned. And next is the coefficient of the operators that we study. And for the coefficients, it depends on whether the operators are generated at tree level or at loop level. So if the operators are generated at loop level for some type of new physics, then there will be a suppression factor of 1 over 16 pi squared. And since there is already a suppression factor of 1 over lambda, so in general, the loop generated operators are kind of ignored with the current experimental bounds. But that is not always true. But for our model, we are only interested in loop generated operators. Okay. So coming back to single top and Higgs. Now, the main purpose of this whole study is whether to find out that the top Yukawa coupling behaves as dictated by the standard model. And for that, we are looking into both the magnitude as well as the sign of the top Yukawa coupling. So single top Higgs and a light jet is kind of one of the very few channels or interactions which provide a probe for the sign or the phase of the top Yukawa coupling, and also the magnitude. And the main reason for that is for some kind of destructive interference that happens between the two Feynman diagrams that I'm showing here. And so basically the two diagrams are with the Higgs Yukawa coupling and the Higgs coupling with any of the vector bosons. So these two diagrams interfere destructively and maximally when the top Yukawa coupling is standard model like. So at the value of the top Yukawa coupling for exactly at the standard model, these two diagrams are kind of interfering destructively. So any deviations that might happen because of the effective operators or the new physics contribution will be effectively shown in these kind of interactions because of the interference. So the goal is to kind of study which operators contribute to these two diagrams, and then figure out how the cross section is affected over a range of the Yukawa coupling, the top Yukawa coupling. So we are interested in the dimension 6 operators because there's only one dimension 5 operator, and it does not play a role in this particular reaction or interaction. In dimension 6, we have a total of 59 independent operators. Of course, that is with respect to a certain choice of basis, and but not all of them contribute to this particular reaction. And among the operators which do contribute, as I mentioned earlier, we ignore all the loop generated operators, and also ignore the operators which do not have any interference with the standard model diagrams that I showed in the previous slide. And that is because if a particular diagram does not interfere with the standard model diagram, the contribution will be suppressed by 1 over lambda power 4, because all these are dimension 6 operators and they all have a suppression of 1 over lambda squared. And so when you're evaluating the cross section, if they have no interference with the standard model, they will be suppressed with the power of 1 over lambda power 4. And the ones which do interfere with the standard model will have a factor of 1 over lambda squared. So we only consider the operators which give rise to diagrams which interfere with the standard model. And after doing all this, there remains only 4 operators out of the 59 that actually contribute to the process we are interested in. And those 4 operators are already listed here. And once we include these 4 operators, the Lagrangian looks something like this. But among the 4 operators that we have, the first with phi and box it only contributes to the Higgs field renormalization. So effectively, it will change the uh, overall factor of the cross section by some constant amount, and doesn't actually affect the single top Higgs production. And the second operator of U phi, or most likely T phi for our, because we are only interested in third generation uh, quarks, that operator in particular uh, essentially just modifies the top Yukawa coupling, because as you can see, there is a factor of phi dagger phi, which along with the very normal Yukawa operator. So essentially, it shifts the Yukawa coupling depending on what the value of the coefficient is. So out of the four, there are only two operators that remain. Uh, One we called O35Q, and there is one 4 fermion operator, O3QQ, that has a major contribution to the single top Higgs cross section from any kind of new physics. So these two operators are mostly what we'll be trying to analyze. And so before I move to some results and analysis, I would just like to mention that these two parameters that we'll be using later, one is kappa t, which is just the ratio of the Yukawa coupling with respect to the standard model Yukawa coupling. And similarly, kappa v, which is again the ratio of the Higgs to vector boson coupling with respect to the standard model one. So it is kind of parametrizing the top Yukawa coupling. Okay, so for the standard model case, without any effective operators, the cross section is already measured and is found to be close to 70 femtobarns. And when we include all these four effective operators, the cross section can vary quite a bit, but the minima remains at the standard model value, because that is where the maximum destructive interference happens. So all the way from 70 femtobarns or 71 femtobarns, it goes all the way up to 500 femtobarns for new physics scale of 1 TeV. And the coefficients of these effective operators are varied between +2 and -2. So, and that is for the Yukawa coupling, which is standard model like, so which is kappa t equals to 1. Next, for the case if we have kappa t equals to -1, which is basically the opposite sign for the top Yukawa coupling, the standard model value of the cross section is much higher, almost 10 times higher. And in cases where I will show some results from CMS, the value of kappa t equals to -1 is kind of excluded with the current available data. But again, if we include contributions from effective field operators, the cross section can vary again all the way from 630 to all the way up to 1400 femtobarns. So the standard model value is not the minimum in this case, and we can actually go lower. So the exclusion limits that have been set up that I'm going to show later for CMS data, and which may not hold true once we include some new physics contribution. And that is kind of the goal to study, that whether we, the limits for the top Yukawa coupling exclusion can be modified if new physics effects are taken into account. And so we are interested in one very specific channel, which is single lepton plus BB channels. So what happens is you have a top quark which decays to a B and a W, and the Higgs boson also decays to a bottom anti-bottom pair. So we have, and the W quark, which decays from the top quark, decays leptonically. So the diagram is shown on the right. And the main reason for this channel is the highest branching ratio for the Higgs going to BB bar channel. But there is also a challenge from a huge amount of background that is available with this channel, uh, which comes from basically TT bar plus number of jets that we include. And it has a much larger cross section, about, I think, around 1,000 to 10,000 times more than the cross section for the signal that we are probing at. So that is kind of a challenging part of this channel. Uh, so initially what we do is we kind of implement some physical cuts on some of the kinematic variables. So most of these cuts are decided based on the detector, as well as so what happens is we kind of look at the distribution for these kinematic variables over the whole range of the parameter space for both the signal and the background, and then put a cut depending on how much we can exclude uh, the background signal without putting much away from the signal events. So for the cuts, what we are using is, since we have at least three bottom quark jets, and so we have put the constraints on the momentum, the transverse momentum, and the pseudo rapidity for the bottom tag jets. And also, since there is only one lepton that is associated with it, which comes from the WDK, we have put constraints on that as well. And what we have for the number of events for the signal and the background are shown in this table. And as you can see, there is a huge difference between the number of signal events and the background events in general. But the interesting thing is for kappa t equals to -1, where you can see the CMS value for this particular kappa t is close to 160 with some amount of systematic errors. And when we apply the new physics effects, the number of events might go down to as low as close to 95, and might also go higher, close to 240. So this range of event number is might indicate that we might be able to kind of modify the currently excluded limit of kappa t equals to -1, or even below that. So this is the graph generated from the CMS paper back in 2019 from the latest run. And what you can see is the observed limit, which is this very line with the dots, and the theoretical cross-section times the branching ratio for the Higgs. And so any point which kind of intersects at kappa t close to -0.9, and so anything above that is still allowed, whereas for kappa t below 0.9 is excluded with just the standard model cross section. And now when we include the contributions from effective operators, we have something like this. So the blue line is the same observed limit that we have from the previous CMS graph. And the black line is, again, the same standard model cross-section times the branching ratio that we saw. Now, the green line and the orange line are kind of the maximum cross-section, and the orange line is kind of the minimum cross-section that is allowed at 1 TeV by varying the coefficients of the effective operators between -2 and +2. So within that range of operators, this is the maximum and the minimum cross-section that is allowed. And as we can see, the exclusion limit that was put from the CMS data can be or might be modified in the presence of effective operators, and values of kappa t equals to -1 is might still be allowed. So that is kind of the whole goal for this project, is to kind of explore this limit on the kappa t. But I would like to caution is that there are a few things which still needs to be done with this graph. And first thing is the effective theory contribution to the branching ratios is still not done in this graph, which I'm showing. But those effects are should be small. And this observed limit that I just copied from the CMS data is kind of model dependent, that we kind of realized later. And we are not sure yet how to incorporate that model dependence. So it might get modified as well. And okay, so I think, so future steps. As you saw that the background to signal ratio is quite low. And there is, even after applying the physical cuts, there is still a huge amount of background that is available, at least in the single top plus BB bar channel. And so the next goal is to use some kind of machine learning models. Mostly, I'm so far focused on the use of decision trees and neural networks. And but I'm not showing any of the results so far because I do not understand them myself as of now. But that is one possible direction. The next might be to look for some other channels. For example, Higgs to gamma gamma, which has a much cleaner signal. So the background is much better, but the question of the signal events is also lowered. So we have to look at how much we are trading off for the Higgs to gamma gamma channel. And so those are kind of the next steps before we can conclude this project. Okay, so coming to the conclusion. So we are looking at the tree-level production of single top associated with the Higgs boson. And it is one of the few interactions which gives us to probe like the magnitude as well as the relative sign of the top Yukawa coupling. And the goal is to kind of study the new physics, how new physics effects are kind of parameterized in this particular interaction. And this can also be used in the determination of the top Yukawa coupling, and also the extent to which we are looking for physics beyond the standard model searches. So by looking at the Torque-Yukawa coupling, we are trying to kind of parameterize how much we can probe for new physics effects. Okay, so that is where I will end for today.
Great job.